Our second unit is called electricity. And of course, to study electricity, we need to know about what causes electricity. This is a basic diagram of an atom up on the board right now. It's not quite correct, it's not quite current, but it works for us in terms of what we're trying to accomplish today. What would you call this thing in the middle here? Yeah, it'd be called the nucleus. And of course, inside the nucleus is what? Yeah, we got protons, which are, what's the charge of a proton? Positive. And what else we got? Neutrons, which are, yeah, they're neutral. Now, the mass of a proton and a neutron isn't quite the same, but it's almost the same. To 3 or 4 significant figures, the mass of a proton and neutron is the same. Now, what is it that's orbiting around the nucleus here? What is it? Yeah, we call this the electron. Electrons orbit around the nucleus, and the electrons have what kind of charge? Yeah, they're negative charge. And how does the mass of an electron compare to the mass of a proton or a neutron? It's a lot smaller. It's like 1,000th or something like that of the value of the mass of a proton or a neutron. Now, in this unit, we're not so concerned with how the masses relate to each other, the protons and neutrons and electrons, but rather we're more concerned with the charges. In our last unit, the masses become a little bit more important, and the difference in mass becomes a little bit more important. We'll still use the mass of an electron or a proton sometimes, but not so much. Again, it's more of a charge thing for us here today and in this unit. Let's define how we get positive charge. I'm not talking about a proton positive charge, but I'm talking about a positively charged object. If you have some kind of object that's charged with static electricity, and you put it against, say, the wall, and it sticks to the wall because it was positively charged, what does that mean? Where did it get that positive charge from? Well, you know that every object has to have protons and neutrons. Doesn't that make it neutral? Sorry, protons and neutrons and electrons. Doesn't that make it neutral? Well, if it's got an equal number of protons and electrons, it makes it neutral. The neutrons wouldn't play any factor in that, right? Because they're all just neutral already. If you have an equal number of protons and neutrons, then it's going to be a neutral object. But if you have more protons than electrons, then you've got an object that has positive charge. So just remember that you're rarely going to see an object that has just protons. It's almost always going to have protons and electrons, but oftentimes it'll have more protons than electrons, and that makes it positively charged. And similarly, if you have a negatively charged object, that rarely comes about from having just electrons. It almost always would come about from having more electrons than protons. And of course, the neutral object is going to have same number of protons as electrons. And again, there's the neutrons in there as well, but usually when we're talking about electricity in the context of certainly this unit, the neutrons aren't usually relevant because they don't add positive or they don't add negative or take away positive or negative. They're just neutral. However many you have, it's not going to change the charge of the object. Now, if we're talking about negative or positive charge, we have to have a way to measure the amount of charge we have. We call the unit of charge the coulomb, just like we call the unit for speed meters per second, or we call the unit for mass kilograms, or we call the unit for energy joules, or we call the unit that measures the amount of electric charge the coulomb, named after a guy named Charles Augustin de Coulomb that we'll talk about a little bit more later on in this unit. We abbreviate that usually by a capital or a big C. Now, if I was to give you a speed of an object, let's say a car is traveling at 50 kilometers per hour, you have some kind of concept, some kind of notion as to how fast that is. Okay, we understand because of experience what a meter per second is, or what a kilometer per hour is, or even a kilogram, or even a joule for that matter. But not really a coulomb. Right? We're not, that's outside of our realm of experience. So we don't really know intuitively, if I gave you a charge of 6 coulombs, like how much that is, right? Is that a lot? Is that a little? I'll tell you that a coulomb is a really, really big unit of charge. In fact, it's such a big unit of charge. Don't write this down. Okay? What I'm going to write in green here, don't write this down. It's such a big unit of charge that it would take approximately this many electrons or protons in order to make 1 coulomb of charge. I kind of lost track of my zeros there. I think I got that right. I think it's 19. Is it 19? Yeah. It takes about 10 to the 19 electrons, or about 10 to the 19 protons, in order to make 1 coulomb of charge. That means that the charge of an electron and proton are both small, but it also means that a coulomb is a big unit of charge. Just like, say, a light year would be a really big unit of distance, a coulomb is a big unit of charge. In fact, it's so big that we often see the charge of an object listed not in coulombs, but in nanocoulombs or microcoulombs or millicoulombs or whatever. But remember, when we go to do a calculation, we've got to be in coulombs. That's our standard unit. So we've got to make sure that we circle the microcoulombs or the nanocoulombs or whatever the case may be in red, or highlight it, or whatever it is that you do. Draw attention to it, and then convert it to coulombs in order to do your calculation. The charge of an electron, okay, knowing that it's small compared to the 1 coulomb, is exactly negative 1.60 times 10 to the minus 19 coulombs. And the charge of a proton, the mass of a proton is a lot bigger than the mass of an electron. But the charge of a proton is exactly the same as the charge of an electron, except opposite sign. Now, charge would be a scalar. When we talk about positive or negative, we're not talking about a direction here. You know, it's 1.6 to the left or 1.6 to the right. We're talking about a type of charge, a negative charge versus the other type of charge, which is positive charge. You got to remember those numbers? Well, I'll tell you what, you're going to use them enough that you probably by the end of the year will remember those numbers, but you don't have to. You can always look on your data sheet, and in fact, you will probably have to look on your data sheet, at least for this unit, because you're not going to have them memorized by tomorrow. To find them on your data sheet, you're going to go over here to the third column under Particles. Okay, you're going to scroll down to under Charge. When you see the electron and the proton, you see it's minus 1e and plus 1e. Okay, that's not what we just wrote down. We wrote down negative 1.6 times 10 to the minus 19 and positive 1.6 times 10 to the minus 19. So what does that mean? What does minus 1e or plus 1e mean? What does it mean? Jack? I heard you say something, didn't I? No? Who was it? Nick? Yeah, you can say it's negative 1 electron or positive 1 electron, but what's the charge of an electron? If you don't remember, it's 1.6. What that actually means, that E, is a term that we call the elementary charge, and you'll understand more what the elementary charge really truly means in our last unit. But for now, I can give you a number for that elementary charge, and it's on your data sheet over here. It says an elementary charge, E, is 1.6 times 10 to the minus 19. So if you want to find the charge of an electron, it's minus 1 times 1.6 times 10 to the minus 19. Or a proton is plus 1 times 1.6. Or an alpha particle, whatever the heck that is, an alpha particle has a charge of 2e, or 2 times 1.6. Or in other words, the charge of the alpha particle would be 3.2 times 10 to the minus 19. Does that make sense? So if you want to memorize those, that's great, but if you don't remember them, that's okay. Just know where to find the charge on your data sheet. And of course, the masses are there as well if you need them. 9.11 times 10 to the minus 31, 1.67, and the neutron you see here to 3 digits is the same as the mass of the proton. A little bit more if we keep going to more digits. It's a little bit higher than the mass of a proton, but to 3 digits, it's the same. Now, I've got, just as a kind of a little final page to this whole charge thing, I've got 3 symbols there, 3 notations there. Okay, I don't really know what you call this notation, but I would call it ion notation. Do you guys know what an ion is? It's like a charged atom. It's an atom that's either lost electrons or gained electrons. This is aluminum. I think they call it aluminium now, don't they? Not aluminum? No, it's still called aluminum? I think it's IUM on the periodic table, though. They changed it a few years ago. This aluminum 3 plus would mean that we have positive charge. In fact, if it says 3 plus, it would mean that the charge of it is 3 times the elementary charge, or it would be 4.8 times 10 to the minus 19 coulombs. Make sense? That means that we have 3 extra protons. Not that we've gained 3 protons, but that we have 3 more protons than we do electrons. And this is sodium. Sodium is plus. That would mean we have a charge of 1 times the elementary charge, or just simply 1.6 times 10 to the minus 19 coulombs. We got 1 extra proton, 1 more proton than electron. This one, O2 minus, oxygen 2 minus, means that we have 2 extra electrons. So we have, what is oxygen? Is it 8? Okay. If we have 8 protons, then we have 10 electrons in that atom, right? Okay, if you have a whole like a whole container of oxygen, then obviously it's more. But in one atom, or I should say ion, it's 8 protons and 10 electrons, 2 extra electrons. The charge would be negative 2 times the elementary charge, or negative 2 times 1.6 times 10 to the minus 19 coulombs. Okay, I want to take a look at your first example for the unit here that's on the sheet that I handed it a little while ago. It says, a balloon is rubbed against hair and it gains a charge of negative 9.6 times 10 to the negative 9 coulombs. We want to know how many electrons the balloon gained or lost. So really we're asking 2 things in this question. What's the number of electrons here, and did we gain the electrons or did we lose the electrons? How do you think you're going to find the number of electrons? Gained or lost, don't worry about that right now. Sorry? Well, you're going to find you look at the periodic table to find the charge of an electron, but that's not going to give you the number of electrons. Yeah? Good. You're going to divide. Okay? If I give you, let's say, let me give you this example here. Let's say we go to Safeway, and I buy a bag of oranges. And 1 orange has a mass, let's say, of 200 grams. And you've got a bag of oranges, but you don't want to count the bag of oranges. So you just weigh the bag of oranges, and it's 800 grams. How many oranges do we have in there? 4, right? We'd say the total mass of the bag of oranges divided by the mass of 1 orange, right? 800 grams divided by 200 grams. I'm not sure if you only had 4 oranges in that bag, why you wouldn't bother just counting the oranges, but anyways, that's how you can do that, right? You can say the total mass divided by the mass of 1 orange. Whenever we're asked to find a number of anything, it's always going to be the total amount divided by the amount for 1. Always going to divide. Always. A number of anything, always divide the total by the amount for 1. So in this case, instead of dividing mass, we're going to divide charge. We have a total charge of negative 9.6 and a charge of 1 electron of negative 1.6. So we're going to say negative 9.6 times 10 to the negative 9 coulombs divided by negative 1.6 times 10 to the minus 19 coulombs. When we do the math there, we end up getting 6.0 times 10 to the 10 electrons. So the number of electrons is the total charge divided by the charge of 1. The number of oranges was the total mass divided by the mass of one. The number of photons, whatever the heck that is, we'll learn about that in our third unit that we call, or fourth unit, sorry, that we call electromagnetic radiation. It's the total energy divided by the energy of one. It's always the total divided by the amount for one. Okay? In this case, charge divided by the charge for one. So the number of electrons is 6.0 times 10 to the 10 electrons. Now, is it gained or lost? Gained or lost? It's gained, yeah. If we have a negative total charge, that means we have more electrons than protons, which must mean we have gained electrons. Does that make sense? If the total charge was positive, then that would mean not that we had gained protons, but that we had lost electrons. It's always electrons that we talk about, gaining or losing electrons. Gaining or losing electrons, not protons. Why is it that electrons move? Why is it that when we're talking about the movement of charge, that it's always the electrons, these puppies right here, that move as opposed to these protons in the nucleus that are moving? I'm not saying it's impossible to get protons out of the nucleus. It's not impossible. But under normal electrical interactions, that doesn't happen. If protons leave the nucleus and go somewhere else, that's not an electrical interaction. That's a nuclear reaction, which is something altogether different here. Why is it, Simon, that it's the electrons that are going to move?
Because the electrons orbit.
Yeah?
And since, well, protons also orbit in the real nucleus, and the electrons orbit around the nucleus negative, I'd say that electrons move off because.
Good. There is an electric attractive force between protons and neutrons. Okay, and there's protons in the nucleus, and then, sorry, not protons and neutrons, but protons and electrons. There's protons in the nucleus, and there's electrons orbiting around. They're attracted. We're going to say the electrons are attracted to the nucleus by an electric force. Sometimes they call it an electrostatic force. Sometimes they call it an electric force. We'll call that Fe. They're attracted to the nucleus by this electric force. Now, we'll learn more about this in a lot more detail, this other force that I'm going to talk about in more detail in our last unit. But for now, I'll just briefly address it. The protons are attracted to each other and to neutrons that are in the nucleus, to both each other and the neutrons, not by an electric force, but by a force that we call the strong nuclear force. I'll call that FSN, the strong nuclear force. And generally speaking, within the context of the atom, not always within the context of the nucleus itself, but within the context of the atom, the strong nuclear force would be bigger than the electric force. So the whole thing wants to stay together, right? The strong nuclear force holds the nucleus together. The electrostatic force holds the electrons to the nucleus, but if something's going to take energy and break free because it's received some energy, it's probably going to be the electrons, right? Because it's the electrons that are not as tightly bound to the nucleus as the protons are, because that electric force of attraction is weaker than the strong nuclear force. Now, we talk about electron movement. It's electrons that are going to move, not protons that are going to move. Let's define a couple more terms here. Conductor and an insulator. In the context of electricity, not in the context of heat. Forget whether it was grade 8 or grade 9. I think grade 8 maybe that you learned about heat. a unit on heat in grade 8 science. You learned what a conductor was and what an insulator was in the context of heat. We're talking about something different here now. A conductor in the context of heat was something that would allow heat to transfer from one thing to the other, or an insulator would prevent heat from being transferred. The context of electricity, a conductor would be something that allows electricity to transfer from one thing to the other. Now, how would electricity, that's kind of a loose term, right? Electricity. Electricity is being transferred from one thing to another. Like, can we be a little more specific with that? What is it that's being transferred, Gage? Yeah, and why are electrons being transferred from one thing to the other in a conductor easier than in an insulator? Well, because they're not as tightly bound to the nucleus. A conductor is a material in which the electrons in the outermost regions of the atom are, I say free to move. That's maybe not a good term. Maybe we should say freer to move. Because all electrons and all atoms can move. It's just a matter of which ones move easier. We define a conductor as a material in which the electrons move easier. They're relatively free to move about. Versus an insulator, of course, which is just the opposite. It's a material in which the electrons are pretty tightly bound to the nucleus. And, well, they can move, but they're not as free to move around as they are within a conductor. It's still way easier to get the electrons off an insulator than it is to get the protons out of the nucleus. But it's not as easy as it would be in a conductor. This next page, I'm going to ask you to not copy this down. Okay, this is out of the textbook, actually, that we used some in Physics 20. We'll refer to it a little bit in Physics 30. We haven't yet, but we'll refer to it from time to time in Physics 30. Not something to copy down, just something for a reference here. You can see on the left-hand side here, we have a column that says relative magnitude of conductivity. In other words, what we're doing with these different materials is not assigning a number to, like, this is its value of conductiveness, but rather we're comparing materials. This is 20 times better or 100 times better or 1,000,000 times better of a conductor than that. If you look at the top here, these ones that we categorize as conductors, what do they, for the most part, have in common? They're metals, yeah. They're generally metals here, right? You could say that, like, silver is a better conductor than copper, which is a better conductor than aluminum, and so on and so on. Gold is a really, really good conductor. I think it's better than all of those, actually. You ever buy a cable, like a audio cable, and it's gold-plated? Like, well, what is that, to make it look nice? Gold is a good conductor. Gold is a really, really good conductor, right? The whole wire, it'd be great if the whole wire was made out of gold, because it's a really good conductor, but it'd be pretty expensive, yeah, it'd be pretty expensive. And a little soft, too, probably, if it was made out of pure gold. We used to use aluminum. Aluminum is a really good conductor. It's really malleable, really soft, really easy to bend. We used to use it for wire in houses. Like, we used to wire houses with aluminum wire. Now we don't. It's against the law now to wire houses with aluminum. It's a good conductor. It's a really good conductor. But pardon me?
Why is it against the law?
Well, we don't use it now because they found that it had this problem of what we call arcing, which means that electrons could arc from the wire to another wire or whatever. And what's the problem associated with that? Fire. Yeah, fire, right? Houses burn down because electrons would arc from aluminum wire. And it still can happen with copper wire as well, but it's less likely to happen with copper wire than it is aluminum wire. And copper's a little bit better of a conductor as well. If you look down here to insulators, what do you notice about these ones? These are nonmetals, right? Wood, glass, rubber, right? And you can see that when you compare the relative conductivities, right? Wood is 10 to the minus 10. 10 to the minus 10. What does that mean? There's no units with it. It's just compared to, let's say, silver that's 10 to the 8. So that means that silver is about 10 to the 18 times better of a conductor than wood. Can wood conduct? Sure it can. Sure it can. But silver will conduct like almost infinitely better than wood will. Does that make sense? Okay, don't memorize these numbers. The big takeaway from this table is simply that metals tend to be good conductors, non-metals tend to be poor conductors. Reason being, metals have electrons on their outermost layers that are freer, right? All right, almost the last thing here, almost. We have 3 laws of electric charge that you're probably somewhat familiar with already. You guys did this a little bit in Science 9. 3 laws of electric charge. Opposite charges. What do we mean by opposite charges? Yep. Positive and negative. Opposite charges will attract each other. Positive attracts negative. By an electric force. Remember we talked about the strong nuclear force and the electric force? Here we're talking about the electric force. Positive attracts negative by the electric force, not by that strong nuclear force thing. Okay, that's another force altogether. But by the electric force, positive will always attract negative. What if we have negative and negative? They'll repel each other. That means they'll push each other away. They find each other repulsive. And finally, we say that charged objects attract neutral objects. The word objects is important because if I have let's say I have a negatively charged balloon, that negatively charged balloon will be attracted to the neutral wall. And a negatively charged object, the balloon, will be attracted to the neutral object, the wall. But if I have a proton inside a nucleus, it's not attracted to the neutron inside the nucleus, not electrically. Remember we said the proton and neutrons are attracted by that strong nuclear force, but that's a different force altogether. The proton and neutron are not attracted electrically. Positive and neutral, it doesn't matter, they're not attracted electrically. But a positive object will be attracted to a neutral object, or a negative object will be attracted to a neutral object. And we'll see tomorrow why you need to have an object as opposed to, say, just a proton and a neutron. For now, for today, for the next 24 hours, well, for the next 23 and a half hours, you're just going to have to trust me on that. Okay? Positive, negative, whatever, are attracted to neutral objects. Finally, for today, I want to talk about the law of conservation of charge. This is kind of outside of those 3 laws of electric charge. The law of conservation of charge. The law of conservation of momentum says, well, total amount of momentum remains the same, right? In other words, momentum cannot be created or destroyed. The law of conservation of energy said energy cannot be created or destroyed. The law of conservation of charge says that charge cannot be created or destroyed. You can transfer it. Well, you can transfer electrons from one to the other. You can make something more negative by giving it electrons, or more positive by taking away electrons, but the total amount of charge will remain the same. You cannot create or destroy charge, but rather just move it around via moving the electrons around. Now, there's a whole lot of places where this becomes important. We're going to talk only about one today, but as the unit and as the year goes on, you'll see more situations in which this law of conservation of charge comes into play. So unfortunately, or fortunately, whatever, even when we're done this unit, you can't forget this law because it rears its ugly head again in the next unit and the next unit and so on. Charge can't be created, it can't be destroyed, it can be transferred from one to the other, just like momentum, right? Can't create or destroy momentum, but you can transfer momentum to another object, take away momentum or add momentum from an object. Okay, let's take a look at an example here. This is example number 2 that's on the handout that I gave you before. It says, 2 charged objects of similar size, shape, and material momentarily touch each other. Now, you're going to see why in a moment that I'm saying that they're similar size, shape, and material. They momentarily touch each other anyways. We'll talk about why this is important later on. The first object initially has a charge of 2 times 10 to the minus 6 coulombs. Well, the second object initially has a charge of negative 3 times 10 to the minus 6 coulombs. What's the final charge on both objects? If one object is really, really pointy and one is round, then you can't really do this question. If one object is way bigger than the other, then you can't really do this question. A bigger object will hold more charge than a smaller object. A round object will hold more charge than a pointy object. But if they're similar size, similar shape, and similar material, when we touch them together, what's going to happen, do you think? They're going to try to balance. They're going to equal each other out. So we're going to say that 2 times 10 to the 6, 10 to the minus 6, and negative 3 times 10 to the minus 6 will balance out to be what? 5 times 10 to the minus 7 coulombs? Or I should say negative 5 times 10 to the minus 7 coulombs? So all you do is add them up and divide by 2. You're taking the average, right? Now, if 3 charges touched each other, what would you do? Add them up and divide by 3. If they touched each other at the same time. You're going to see a question here in a moment where one touches another and then one touches another and so on. In that case, you can't just add them up and divide by 3. Okay, if they touch each other at the same time, then you would just simply add them up and divide by 3. Which object gained electrons? Which one gained electrons? Well, listen, they both became negative 5 times 10 to the minus 7. This one was positive. Did it gain or lose? No, it gained. It was positive. If you're positive, how do you become negative? You gain negatives. So this is gained electrons. I use that symbol a lot for electrons, by the way. And this one, well, this one is negatively charged. It's still negatively charged, but it's less negatively charged than it was before. It's 10 to the minus 7 versus 10 to the minus 6. So this one has lost electrons. If you're positive and you become negative, you gain electrons. If you're negative and you become less negative, this looks like it's more negative, right? 5 compared to 3, but it's 10 to the minus 7 compared to 10 to the minus 6. It's less negative, which means it's lost electrons. And the very last thing, example number 3, which is on that handout as well, says ball number 1 has a charge of 3. Ball number 1 touches ball number 2, which initially has a charge of minus 1. Then ball number 1 and 2 are separated, and then ball number 1 touches ball 3, which has a charge of minus 5. What's the final charge on all 3 of them, assuming the balls are all equal size, similar shape, and similar material? So that whole similar size, similar shape, similar material, basically identical objects. That means that we can trust that they're going to balance out when they touch each other, right? That's normally what's going to happen in this type of question here. To figure this out, I want to create a little table. Initially, I have 3 charges that are plus 3, minus 1, and minus 5. So before anything happens, these are my charges. Add them up, divide by 3? No, because they're not touching each other at the same time, right? Cal, what do you think I'm going to do there? Yeah, good. 1 and 2 are touching each other. So let's add those up and divide by 2. Let's figure out what they balance out to be. Plus 3 minus 1, it's going to be, what is it? Yeah, the average is going to be 1. Right, 3 plus negative 1 divided by 2 is plus 1. And then what does this become? It's still minus 5, right? Nothing's happened to that one yet. Then it says ball 1 touches ball 3. 1 touches 3. 1 and negative 5 becomes negative 2 and negative 2, right? 1 plus negative 5 divided by 2 becomes negative 2 and negative 2. What about the second one? It's plus 1. What's the final charge on all three of these balls? Plus 2 coulombs, plus 1 coulombs, and minus 2 coulombs. That's a lot of charge, right? We said a coulomb is a big unit of charge. Oh, whatever. If you're dealing with something that's in microcoulombs, you could do with 2, right? Just like we did in the last question. It has more exponents, that's all.